So my name is Jim Rain, and so I'm going to spend just a few minutes here this afternoon telling you about programmable logic. So some of you I know in the audience are already well off and understand programmable logic, and so for those of you, just try and not cringe too much because I'm coming at this from maybe a little bit different scenario. So for many years I've been working on designing computer projects primarily for the Commodore platform, although today I'm going to tell you about a device I've been working on for the Tandy color computer. However, the things that I focused on initially are microcontroller-based projects. So if you've been to the area in the main hall, you've seen some of the projects I've been working on. You typically use Atmel AVR microcontrollers, and you get a lot of mileage out of the newer microcontrollers. Run up 20 megahertz, some of them run at 80 megahertz and so forth, and so you can do quite a bit. And I've got a lot of mileage out of those projects. However, some of the things that I work on, like network device, interface cards, and so forth, require discrete integrated circuits in order to operate. For the Commodore environment, and as well as for some other environments, there's a predominant Ethernet integrated circuit that's used called the Cirrus Logic CS8900A chipset. Many of you are familiar with that chipset. And so in order to interface that to a Commodore or Coco or an Apple or something, you do need to put some glue logic in place to convert the non-Intel type of addressing logic and memory read and write capabilities into the Intel type read-write capabilities. So there's definitely some things that microcontrollers are not great for, and so I started down the path of using TTL logic, which I know a lot of people have done in the past. What I found over probably the last 5 years is the community has gotten more encouraged by the number of projects that have come out and the capabilities in those projects, and so there's always an increased demand for capability. And obviously the cost of components is not necessarily going down. And so if you do discrete components, you can end up with a great solution that's not marketable. So it's got, in the case here, I put up on the screen, this is a solution that somebody developed called a multi-pack interface, which is basically an expansion interface for the Tandy color computer. This is one particular project that was put together, and I just pulled it down because it's kind of indicative of this person used TTL logic in order to build this particular unit. And as you can see, it's got a whole host of TTL chips that are necessary in order to build this. Of course, a big board that's necessary to put it together, and by the time you're all done, you end up with a solution that's probably, it works fine, but as from a marketing standpoint or from a sales standpoint, it's very hard to put it into everybody's hands at an economical price. So not everybody wants to spend $200 or $300 to buy basically an expansion box for their Tandy color computer. So I'm starting to see this as a big deal, but one of the things that I was challenged with is to move to the next step in the evolution of designing hardware projects required that I understand what's called programmable logic devices, or PLDs. And many people probably don't know that terminology, but basically they are logic devices. They are integrated circuits that you can put on a circuit board, and these devices come with a matrix of gates inside the integrated circuit that you can program to decide what those circuits are going to perform as. And so the advantage is that you can, at design time or at runtime, you can, or not runtime, but at design time, you can decide how you want that particular circuit to work. The downside is you have to actually program it, much like you would program a microcontroller to do the stuff that you normally do from a computer standpoint. There is a little bit of a learning curve. So today I was just going to give everybody kind of a feel for how I got from not knowing anything about complex programmable logic devices to where I am today, which I've got some projects sitting out in the show floor today that appear to be working, or at least more working than not, that use CPLDs. And then, of course, this is kind of the CPLDs are kind of the gateway drug to a technology called FPGAs, which I'm sure a number of people have heard about, and some people use in some of their projects. FPGAs are kind of the larger version of CPLDs. They're a little bit different, but a lot of the foundational aspects are the same. The difference primarily is performance or capability and priced. So CPLDs typically can be purchased, the chips can be purchased in the $2 to $5 range, and FPGAs typically start at $10 and move significantly on their way up to $10 or to $20 or $30 or $40. But then again, they have quite a bit more capability. So I'm not going to talk about FPGAs today, although some of the things I talked about today are equally valid for FPGA development. So one of the things I want to tell you guys is I think everybody who has any ability to program in this room can pick up how to do complex programmable logic devices. Sorry. The key is you need to understand how to get into this. And I'll be honest with you, I thought the learning curve for putting this together was going to be very hard. So I'm going to just kind of show you today what it takes to put a CPLD project together, just very quickly. Like I said, this is an early one of the designs for a Coco multi-pack interface MPI. And so I just decided to, it seemed like there was an opportunity to make something like this and kind of learn how it worked. Didn't want to do something in TTL logic like this, so I decided to try and do my hand, or trying to create the project using CPLD. So the first thing I did is, obviously, I need to design a schematic, and so one of the things I did was I started working on an idea for this unit, and so I'm going to bring it up right here. I use Eagle, so it's a unit. It's a package that I've used for quite a while. And so I'm going to bring up the Eagle schematic view of the unit right here. And so as you can see, the large item on the screen right now is a CPLD. It's a big chip, and it's got a bunch of signals coming into the chip and outside of the chip. But probably doesn't make a whole lot of sense until you look at it from the PCB perspective. So this is one of the things that you want to start with is a schematic. Now remember, a CPLD is a programmable device, so you don't have to focus so much on how to use the device. You just need a footprint and the schematic version of this, and then you can start laying out a device. Now this looks like pretty complicated here, but the majority of this particular device is just a bunch of wires, because this is a four-position expansion interface, and then just some IDE cabling that connects this daughter board, which has got buffers, to the main board, which has the actual expansion ports in it. And then, of course, as you can see right here, there's some integrated circuits, some TTL logic down here, and I'll explain that in just a little bit. Voltage regulator, and then the main chip of the day is the CPLD that's sitting on the main board. And then I'm going to go ahead and I went ahead and actually produced this board. So I've got a number of copies here. I'm going to send 2 copies down each side, so you guys can start looking at it. Feel free and
get one back.
Well, no, you got to give them back. I want them back. So anyway, so I started with this design. I had a CPLD that I put in place here, and then that's kind of the same thing that I've been doing for years as I've been developing hardware projects. So put the schematic together, put the printed circuit board together. Now then comes the real magic happens, and that is how to turn an actual design into reality using a CPLD as the main part of your project. So one of the things I'm going to talk to you about today is I use Xilinx. There's 2 main CPLD and FPGA vendors. One is Xilinx, the other one is Altera. There's pros and cons to each one. I seemed to get a couple people that were already using Xilinx, and so I decided to go ahead and start down the Xilinx path. But if you want to go down an Altera path, that's equally valid.
Or a Lattice path.
Well, yeah, I guess a Lattice, although I don't know as much about Lattice. Any of those paths are fine, but I'm going to talk today about Xilinx. So Xilinx has a free piece of software that you can download. It's called ISE Webpack, and this is what it looks like. It looks very complicated, but when it comes up, this is what it shows. And I just want to tell you that this looks complicated, but the way to start a project here is you simply say new project, okay? And so assuming that comes up here. So what you want to do is just type in a name for your project, and right here, just say HDL, and then once you type in your name of your project right here, then you can go to the next item. Yeah, that's right. And then it'll bring up a unit here, and you can just go right here. This is where it starts out, and you can say new source, and you can create a piece of source code. And this is the magic right here, is I put Verilog module, okay? Verilog is a type of programming language that you can use for high definition language. There's two different languages that you use. One is Verilog, the other one is VHDL. Interestingly, VHDL was created in the United States, but it's used more prevalently overseas. Verilog was created overseas, and it's used more prevalently in the United States. I don't understand why that is, but I use Verilog because I'm a C programmer from days on past, and Verilog looks a lot like C to me. So I would say if you're a C programmer or Java programmer or whatnot, it shouldn't take you too long to get your hands around the idea of writing Verilog code. Anyway, so one of the things I wanted to point out when you do Verilog code is everything is a module. Basically looks like a function. For those of you who've written C functions, you can see up there top it says module, and then you've got a bunch of variables. Just think of each one of these variables as one of the pins on the CPLD, right? There's some tricks you can do. If you see right down here, there's an address. There's an address input, and there's actually 10 bits in that address input, so it's actually an address bus. So that's the way you do address buses in Verilog. But the real meat and potatoes here is these statements right down here, and some of this is just syntactic sugar. But here's something right here, and you should be able to figure this out very quickly. Basically, this is saying this output is equal to this input. So basically, it's tying those two together. And you can use any kind of logical expression to do that. So if you see right here, you can see this one where I say RAM select equals not RAM 1 or not RAM 2 or not RAM 3. So if you know anything about logic gates, basically you're saying take the value of RAM 1, negate it, or it with the negative value of RAM 2, or that with the negative value of RAM 3, and that's the output pin. And so what used to take an OR gate, and I don't remember the 7400 logic number for an OR gate, but what it used to take an OR gate and then some 7404s is now just that statement right here. So now, I'm sure there are much faster, cleaner, neater, nicer ways to write some of this Verilog code, but I'm still early in the process. So you'll just have to bear with the fact that my Verilog probably looks like people's C code does when they're still learning how to write C. And this particular project that I'm working on right now is, I've got some debugging stuff in here because I'm actually working on debugging this earlier today, and just so that you all know, it's this particular project is working very well right now. I got it working a couple hours ago. But anyway, this is some of the stuff that you can see from Verilog. And so a lot of here you can do things like, some people who know C code should be able to recognize this. It's a ternary operator. So you say if the first value is true, then the first part of the statement is selected. If not, the second part of the statement is selected. One of the things that I wanted to point out here is most of this stuff is just assigns, which basically is just combinational logic, or combinatorial logic. Okay, thanks.
Are you speaking back?
Somebody's got one left. But one of the things that I want to talk about is one of the things that I'm always having challenges with as I try to develop more complex projects is the idea that people need to be able to store data in registers, or they want to be able to store, they want to be able to set and change the behavior of certain things on a board. It is complicated to build I/O registers using TTL logic on small hobbyist boards. I mean, you can do it, but it takes a significant amount of support logic and can really wreak havoc on a budget if you're building a product to sell in this marketplace, a hobbyist marketplace. So one of the things that's nice about CPLDs, although they're not necessarily designed to do all this, one of the things that's nice about CPLDs is it's relatively easy to create I/O registers in the CPLD environment. And so one of the things I'm sure you've used for any kinds of expansion cards or whatever, you can set values. You can set the on the CS8900A, which is the Ethernet chip, or an RS-232 chip, for instance. You can set what the baud rate is. You can set the stop bits. You can set the packet size. Those kind of things. So sometimes you need to be able to set registers to say, hey, I want this particular I/O chip to be in an address space at this byte or at this at this area of memory as opposed to at the bottom of memory all the time and whatnot. So one of the things that you can do in this case is you can create registers. Now this particular thing, it says register, which is a thing that I've defined, and if I click on it here, it will load up another piece of code, which you could load in line. But this is the real trick of using non-combinatorial logic here. This is as you can see here, this is a special kind of notation. And basically what it's saying is I want you to actually create some flip-flops, right? I mean, at the end of the day, I want you to create some latches or some flip-flops, and I want you to be able to store some data inside the system. So it's not just combinatorial logic, it's actually something that's going to hold its state when I get done. And so the nice thing about this is, so we got a negative edge going clock here or a positive edge going reset. And as you can see, the code is very, very, very simple. If reset, this little thing right here says assign the reset value to the output, which is Q. Q is defined here, and the output is right here, Q, which is, in this case, it's width minus 1. Width normally is 8, so it'd be 7 to 0 or an 8-bit register. Q is a value that can be stored to it in reset state. Normally it's set to 0. But if the enable is turned on and the negative clock happens, then assign the D value to Q, which for those of you who know a flip-flop or latch, that says assign the output to the input and hold it there. And so a little bit of quick code right here. I did not think this up. Basically, I went to vlsi.helpme.com or whatever it was, and I pulled it down. And I mean, I understand it now, but I would suggest that if you're just learning how to do Verilog, that there's definitely a lot of help online that you can just go and grab this code from and play around with it and get it to work. Once that's in place, then you go back here and you say, hey, I want to just wire it up. So if you look here on this register, the first one, for instance, I pass in my clock signal, I pass in my reset signal, I pass in a thing that says, okay, how do I want this to be enabled? And the case here is this is a cart config 2 register CE, which is basically a combinatorial definition that I defined up above. And the definition up above basically says it's right here. It says I'm going to write addresses, and the address is set to 0. The address 2 to 0 is equal to 0. And that's all there is to it there. I realize that it still looks a little daunting, but I'll be honest with you, when I got to this point, it seemed like it was a lot easier. But then I ran into one challenge, which is you get to this point and you go here and you say, you know what? It's time for me to compile all my code. And it's going to go ahead here and compile the code. It's going to compile it down to a .jed file or a Jtech bitstream file that can get loaded into the CPLD. That is probably where I stopped for a while, because this program was easy to load up. It was easy to find samples on Google. It was easy to find samples on VLSI Help Online or whatnot. But then what do you do to actually turn it into an actual program? How do you get it actually on the board? So I'm going to show you, so you all saw the board right there. I'm going to show you a board I have right here, which is a flash cartridge board. It's probably hard to see right here, but you can see there's 2 chips on the front of the board, and then there's a little wire hanging out the side. This wire hanging out the side is what's called a Jtech port. Okay, so the Jtech port is really important, and it's really important because, so this thing's done, and it says, hey, I took care of compiling everything, I got it all ready to go, and then it says, okay, well, now what do you do? Well, here's the next step, and I figured out the next step, which is to load up this program called Impact. So if you use the Xilinx tool, Impact is your friend. That's how you actually get the code to go into the CPLD. And what you need to do is you need to go on eBay and you need to buy one of these units. I just priced them this afternoon, and they're $20. So if you have $20 to spare, you can buy one of these things and plug it into your computer. There's a DLL that's already loaded when you load the Webpack software. Installs, and then all of a sudden you have this platform cable right here. And on the end of it, there are these, it's a 2x5 connector right there. And so magically that 2x5 connector goes right onto the end of this connector right here, which are there's 4 I/O signals that are always on the CPLD port. You just run the wires out. And then there's 3 volts, 3.3 volts or VREF and ground. So that's your 6 signals, right? So once that was done, I'm not going to do it. I can show you, if we go back to the main hall, I can show you this operate right here. But basically, you go over here and there's a thing that says, you can just open your project, and there's a part here that says wizard. There's a wizard that shows up. I think it's under file when I first bring this up. If you do the wizard, it'll find the cable. If you have it plugged into your little chip, it'll automatically find the chip, and it'll come up with the chip here being green, just like it is right now. And then look, you right click on it and you say program. And that dumps all the code right into the CPLD. Now, chances are your program won't run the first time, right? So just bear, it's the same as when you're writing software. But what do you dump it into, right? You don't want to have to go through all the trouble of writing up or making up a schematic or putting together a PCB just so you can try this out, right? You want to do this probably pretty easily. You want to probably get into this before you sink a lot of money in it. So what I also did before I actually built the Tandy MPI design is my first foray was to buy one of these boards right here. They sell them on, I checked on eBay this afternoon. This is a small 72 macro cell CPLD from Xilinx on a little board with a voltage regulator. It takes 5 volts coming in. It's got a little reset button or a little on-off button, I think, on it. And it's got a little thing for the Jtech Board right already on it. So you don't have to do anything special. You just plug the little cable right in like that. So you have right there, this board's $10 on eBay. So I highly recommend that, right? This is the way you can try out a few things, try out some code, see what works, and then you can, it's got the little headers, and so you can get those little Arduino jumpers, and you can put some LEDs on it, you can see what's going on, put a clock signal in there. That's the way you can test out your code. That's how I started with this thing. So once I figured out this impact program, and I had these two pieces right here, I had everything I needed to start working on CPLD. The one other thing that I would suggest everybody obtain, if you don't already, is there is a bunch of, I would say, knockoff or cheap logic analyzers, software logic analyzers on eBay. Actually, you can get them a number of places, but this one I purchased off eBay. I priced it at about $15 for a logic analyzer. There's only 8 channels, right? But that's enough to get started. There's a piece of software that's freely available. You can put on a Windows machine. You run this thing right here, and then you end up with this. You end up with a complete project. And of course, once you get done, and once you've got a little bit of success on doing Verilog, which, like I said, looks suspiciously like C code, then you have the capability of starting to lay out boards like this and put units together. So one of the things I wanted to point out is, as I showed you initially, there was that PDF and it has all those TTL chips on it. This is a replacement for that particular project. And as you can see, with the exception of these buffer chips over here on the front end, the CPLD is the sole IC on this design, right? So, I mean, there's one, I guess you call the voltage regulator another IC, but that's it. 2 ICs are it. So you can get the project down from being 12 or 15 TTL logic ICs down to a single complex programmable logic device. And to me, that's a good trade-off. Not to mention the fact that on one of the other design, one of the nice and exciting things about CPLDs is happened right before I came to the show. So I got this design all done. I got the board all taken care of. I got it all soldered up. One of the things that's on this board is a 4-position switch. Right? There's a 4-position switch. If you go and you look at the unit, I all soldered up. There's a 4-position switch here, and the 4-position switch is set up so that it counts in binary. I've configured it so that, you know, in one position, both of the signals or both the switch, double pole, 4-throw switch, so both of them are low, and then the next one's up and one's down, and the next one, the other one's up and the other one's down, and then the last one, they're both not shorted out. Well, lo and behold, evidently I can't seem to remember how binary works, so I got it backwards. Right? So I went up, flipping the switches, and I went from 1 to 3 to 2 to 4, and I'm thinking, what's going on? So one of the neat things about CPLD is, and I'm going to show you one final thing before I finish up here. The one other piece that you need when you start working on one of these projects is that you need to define what pin, you get to define what pin to use for what signal. Because the program, as I showed you there, let's see if I can get this to go. Oh, this is the other program. So in this program right here, I had that schematic, and I showed you the schematic with all of the pins laid out. And so in this program here, I showed you at the top, I showed you all the inputs and outputs to the program, right? So they're right here, all the inputs and outputs. You got clock, reset, and so forth. One of the things I didn't show you is this piece right here. And so it's going to bring up another program here, hopefully. Okay. So here's my CPLD. And you'll see all the names of all the I/O lines right here on the left-hand side. And then here's a picture of the CPLD right here. Now the yellow, green, and red, and pink boxes are special. But the ones that are just circles are ones that you get to use. And so all you have to do is just drag these from one place to another, and you can change what pin is equal to what signal. So what I did, so I had it all laid out, and I had it laid out so it matched the schematic, but then I realized on Friday that I had the 0 bit and the 1 bit messed up. Normally that'd be another spin of the board, right? Or I have to cut the traces and whatever. So what I do is put it in right here. I just said, you know what? I'm just going to put this one here, and I'm just going to put that one there, and I'm done. Right? So it makes it a lot easier to change things after the fact without having to change the board design. So definitely a boom for programmable device.
That's after the chip is already soldered, you reprogram it.
That's right. After the chip was already soldered, the design was already running, it was already doing things, it was doing them wrong. So I thought, you know what? The easiest way to fix this for the show is just to flip the 2 signal names in this floor planning capability here. And then if I decide to do another board spin, which I may, then I'll change it in. But I don't have to come to the show with having everybody say, Jim, you know, your project works, but it goes from 1 to 3 to 2 to 4. So unless I had told you that day, nobody's going to learn that. Right. So I would say, I encourage you all, if you are looking to do hobbyist projects and whatnot, I encourage you to look at programmable logic devices, CPLDs, either Lattice, Xilinx, or Altera. Obviously, I can probably provide more help with the Xilinx, but I've been very impressed with the capabilities of these. They're reasonably inexpensive, and I'll be honest with you, after having to lay out boards that, a lot of the cartridge boards are really small, like a Commodore 64 cartridge case or whatnot. You don't have so many chips inside one of those. It makes it a lot easier to make projects that are interesting to the community if you just have one CPLD and you can put a whole bunch of capability into the unit. The downside of CPLDs, with the exception of some of the very early models that are PLCC packaged, which you can buy sockets for, most of them are QFP type packages, so they're a little bigger to solder. So I have to say there's some good parts of this, there's some not so good parts of it. Soldering is probably the least fun part of CPLD development. But the idea, obviously, is that I think this particular project, for instance, which they're testing out in the main floor right now, which is the multi-path interface with the Tandy Turbo, or things like flash cartridges for various platforms. Those are much easier to do, in my opinion, and it's much less stress on the designer if you can take advantage of CPLD efforts. So, any questions?
Yeah, 5-volt versus 3.3. 5-volt.
So right now, you can't. There are a couple of manufacturers that still make 5-volt CPLDs. Most of the things you're going to find are 3.3 volts, but they have 5-volt tolerant logic. So that's probably the most prevalent. Like the units, the Xilinx parts that I'm using are 3.3 volt units that they'll handle 5-volt I/O, which still works okay for most of our platform. However, some of the units don't, and if they don't, then let's see. I'll bring up the schematic here real quick. So in the unit right here, you'll see there's some buffer. Whoops. So there we go. Some buffer chips down here. So in this particular case, it was easier to put some dedicated buffer chips right here just to make sure that the signals are all nice and cleaned up. Predominantly for 2 reasons, not just for the CPLD. In this particular case, these 2 boards are separated by a long cable, and so the buffering helps with signal integrity. But you can buffer, you don't have to, on the 3.3 you have 5-volt tolerant input. But some of the newer styles that definitely FPGAs do not have 5-volt tolerant I/O. There are a number of buffering chips that have multiple voltages. You can use 1625, something like 16251. I can't remember the number, but it's like a 16-port
buffering chip you can put on the device, and so that helps you out considerably.
There's two types. There's dual VCC buffers.
Yeah.
Which have an A side, B side, and runs on the rails.
Yep.
And then there's also what's called a quick switch, which is simply just to accommodate that, where both sides are normally high in beats until one side pulls it down, goes down the other.
Yeah.
The downside of quick switches is you can't see large amounts of current because the current still sunk through your FPGA I/O. So for an omnibus interface or something that has like a 20 to 40 million drive,
So that's where you use dual rail.
dual buffers.
The problem with dual rail buffers, I think, is they're not bi-directional, right?
They usually go all direction and on the other direction for the drive.
So you do have to do some work when you're buffering with the outside world. Luckily with CPLD, that's the reason I think CPLDs are nice, because at least in this space, you can get by that and have to do a lot of complex buffering. Getting the FPGA space, that you're definitely in space. You definitely have to do something to connect yourself to the outside world.
And TI makes the dual voltage buffers in the as well. You still don't have to see. So they get down.
There you go. Any other questions? I know it sounds daunting, but I really encourage everybody. A couple of years ago, it's taken me about a year to learn how to do CPLD development, and that's learning Verilog. That's also learning how to use this tooling. So it's been well worth it in my opinion, because the number of projects that are opened up now is significantly more than I had. I was kind of running out of steam in the discrete CTL options. This gives me much more headroom to work on projects and add all these cool features that people say, what do you need if you could add just one more thing to the project, right? Because that's the thing, if you design the board and you leave a little bit of space in your CPLD at the end, now I don't know how much a little is fine, but once you do, then if somebody says, could you just add one more thing in, then you're going to be able to do that. So, appreciate it. You can take a look at the project outside.
Another useful trick on the Untitled card. I used one in a very country cartridge. Is that these Untitled cards have bus keeper circuits on their I/O. So if the pin is high, we could pull the pin high, and if the pin is low, we could pull it low. And a nice trick with that is that if you are ever trying to interface with something where you don't have read-write signals, but you know whether something's being better written, then you can then the bus keeper circuits can allow you to make it so that in this particular case, I took advantage of the fact that the bus was transmitted for the first half of the cycle. So what I did is, for the first half of the cycle, read by the memory, and it goes on the bus, and then gets weakly held by the bus keeper circuits. And then in the second half of the cycle, write that by the memory, write what's on the bus, back to memory. And so if the processor was doing a read, then it would have been pulling the bus. And so the bus keeper circuits would just pull what had just been read from memory. And so that was a nice feature for the Xilinx card, but
there you go. So definitely have a number of options depending on which one to do. But I would say initially, just to put combinatorial logic and some registers and thing, it would be a great thing. Okay.